Okay, we're gonna start the second lecture, and the Monday, I really talk about the overall coverage of the course, how I'm going, what is my thought on this course, what I want you to do with the course, with the young Shin, vice versa. And today I'm going to spend just a few minutes on this, and I'm going to move on to chapter 1. Chapter 1, you already have chapter 1 copy, the file by email, right? Yes or no? You have a copy. And also chapter 1 appendix is that you have it already. So you have a 2 file that I asked Higyu to send it to you. So all of you should have a 2 file. But the chapter 1 appendix is very basic, like introduction level for a classical vibration problem. It's really a beginning of a vibration problem. I feel you still need to quickly review what's in there. Okay? For example, you know already like decibel. So think about it. Decibel, of course I know. Do you just know equation set? Or a little bit more, even in applications. Mean square value, that's what you are using it all the time. Or RMS value, root mean square value. So all the definitions are in there. In that intro, chapter 1 appendix, it's a few pages, I just summarize it. That's my lecture note when I taught the vibration courses. But random vibration, I am of course going to really bridging to a knowledge together, of course. So some additional files, I'm going to send it to you just for your references, okay? That's what we're going to do. The textbook I said, but I just call the textbook, but this 4 books you can readily access to review, or you see me anytime. Whenever I teach, you has a top priority. So you can come in anytime to my office. So then we can discuss it, whatever your question is. As I mentioned, if I can't answer, I have to also investigate myself. Then I'll let you know when I really find what's going on. Same thing could happen in the class also. So we're gonna learn together. That's the idea. This stochastic process of structured systems, I really generate or create this course about 20 some years ago in Naval Postgraduate School, and control peoples, structural dynamics peoples, that's what they are taking these courses. So here I start offering since last year. And the first book is written by Dave Newland book. He was a professor from Cambridge University in UK. I met him in the conference. This book, I really like him. He added one additional topic, is wavelet analysis, but I'm not going to really cover the wavelet analysis. This wavelet analysis is also somewhat useful for other application. So for the stochastic analysis or random, the analysis, the spectral analysis and the random vibration, that's kind of the focal point on this course. And the reference one, the probabilistic theory of structure by Isaac Elishikov, he is some person. He's a good friend of mine. He graduated under the direction of Professor Bolton in Russia. Very well-known probabilistic structure dynamics kind of the work. And he is a distinguished professor at Florida Atlantic University at the present time. So I hope he has a chance to come out to KAIST sometime really this year. I really suggest him to come to a conference this September in Seoul, Korea, and myself and Pilsen Lee and Professor Hyun Chung and also Professor Paul Berrigan, we are organizing the conference up there. So maybe your thesis work could present. It's all related to ocean engineering, ocean systems engineering. So that book I am using a little bit to, he has some good concept in the particular area, so that's what I'm going to use it. And this engineering applications of correlation and spectral analysis by Bandad. Bandad, he's about between 85 to 90 years old mathematician. I know him for about 20-some years. I'm sure he's still alive. He's a fantastic person, really fantastic person. But usually fantastic person is very stubborn person, you know. But it's really enjoyable. He visited my school when I was in U.S. So Alan Piazor, very nice person, but he passed away 2 years ago. So, but this is more engineering type of the person. He's a mathematician. Combining two together, it generates the beautiful book. And this is very fundamental random data and analysis book. So I have this, I have that, I have all that. And book 3, this is again similar topics by Paul Wershing. He used to be a professor at Arizona State University, and I know him over 30 years. I think he's retired. He's slightly younger than I am, but we're all older persons here, but slowly fading away. So it's good to capture the things they know. And it's again, this textbook is good in a sense. It arranged very systematic way. Time domain problem, then frequency domain problem, then some additional topics all the way with applications. So this, I don't insist you must read from the beginning, from the first page. No. When the question arises, this is a good book to look through and find the area, then spend a little bit time to read. That's my idea. That's why I don't want to really say, this is the book you must buy. No. So if you know, we're supposed to have 8. We have one more. Who is here first time today? I think maybe you are the first. So did you register? Okay, you just snoop here then to check who is the guy teach the this. Well, just feel free. Okay, feel free in this class. In the class, just feel free, talk anything, but don't shout at me. But otherwise, you can talk anything. I'll talk anything. There is no such a thing as misunderstanding. Okay, I hate such a thing. Then just we'll talk. That's what we're gonna do. And I hate to give exam, but teachers, they have to always give exam. I hate to evaluate the person, especially KAIST students. But again, somebody pointing me, Youngshin, you must give exam and you must grade it. You must give a good grade, right? So I'll give you midterm exam. I'll count as a 30%. That would be good. Which is 8th week. Okay, 2-hour exam. That's what we're gonna do. Usually close the book in the first exam. And then another exam, of course, is a final exam. Final exam, I haven't decided what I'm going to do this semester, but could it be closed book or open book or take-home exam. Take-home exam, I'll think about it because you suffer more. Why? Take-home exam is more difficult, but usually I don't do that. Even take-home exam, you should be able to finish in 2 hours. And if you cannot finish in 2 hours, if I give you 3 hours, the results are same, no differences. That's what I found out. And again, all the exam is very comprehensive exam. If I want to kill you, I can just make up the problem. You can't even touch it. Then I can just zap everything 0 out of 100. But that's not the purpose of the exam. The purpose of the exam is really to check out whether you fully understand all the basic stuff and things like that. That's what my philosophy is. Of course, each professor's teaching philosophy is different. So, you know, it's up to the teacher. So the stuff I'm talking is just my idea, and that's the way I handled for the last 30 years. So that's what I want to do. And the grading, always students has interest on grade. And my philosophy is I don't care about the normal distribution of the grade. I say, oh, out of 8 people, then by this normal distribution, only 1 person, he should get A. But my philosophy is different. If everybody's doing well, everybody will get A. If everybody's not doing and they just have a great time outside of the classroom, then they all have C. I rarely gave a D. I rarely gave even C. For graduate students, graduate work, if you have a C in the state, in US, usually the teacher will kick the person out if he come in with a grade C or below in the previous semester. So C means a failure in graduate studies. So I don't expect anybody here in this class has below B. No, I don't want that. Sometimes it's the teacher's fault. How they can, in such a small class, how the person can have C grade. So the way I handle is, if everybody get good, performance is great, then everybody got A. Everybody not good, everybody get bad grade, vice versa. No probabilistic distribution for the grade, okay? Another maybe example I'm going to tell you for a minute, that tells you what my philosophy on the grade. The Naval Postgraduate School, where I taught for 30 years, it's all officers are there. Naval officer, Army officer, Air Force officer. It's all mostly officers coming for mostly the master's degree, and some, as you are doing here, some, of course, doing the doctoral degree. Then one student, his name is Gary, he is in Army rank here is a major, which is pretty high rank. And Gary is a very good engineering duty officer, and he, in the midterm exam, he couldn't perform at all. And midterm exam, almost zero. I don't know why. So during the exam, I didn't know. Then after exam, I look at his paper. It's front and back, whole sheets are blank. Nothing he did. So after, when I grade, I discovered that. Then I called him up to my office. I said, how come you couldn't do even a single problem? What's happening? He confessed to me, when he looked at the problem set, his mind just went blank, zap. He couldn't think. He kind of shivering. Once he started shivering, nothing he can think in his mind. So I check his overall grade. Then he's the leader, you could say, or program leader, who is a colonel. In Navy is called the captain. I talked to him. Then he mentioned, if he got your grade, your course, the B minus, then he can graduate. If he cannot graduate, means the chances are he must leave Navy. That's the end of his career. Gosh, it bothers me. If I give him B minus, if I give him like a C plus, his career ended. What should I do? What should I do? Already, midterm exam, he flunked out. So then I give some thought, and I really pray for him. Then I told him, Gary, don't worry about the midterm exam. You just sit tight and solve the problem, but you don't have to solve in 2 hours. And why don't you go back to your office? They have small cube like you have, then solve here. I don't care how many hours you spend and solve it. Then if you do really well, I will reconsider it. So he did. He performed really well. When you just sit back in the free environment, then he has a good time to think. He doesn't have to worry about the time limit of 2 hours. So final exam was take-home exam that time. He performed really well. So I end up giving him B+. I don't forget that. Then what happened? I have some chance to tour the aircraft carrier a couple of years after. That Gary, the same person, he was a chief engineer for that aircraft carrier. So think about it. He's a savior. I'm a savior to him, right? So, gosh, I was like, the way he handled me is like, I'm like a king. They come in the morning and he took me and see all the engineering compartment, reduction gear systems, everything he explained, and I felt so wonderful. I gave him B+. That's some joke anyway. So that's the way I'm gonna handle the exam problems and the grade. Okay. So is it clear how I handle the grade? Okay. Chapter 1, and there's a phone numbers here, fax numbers, and the email addresses, and also that's a school phone number 1592, and my hand phone number 010-8956-1592. You may call me anytime, and you may also send me the email anytime, but don't call me after the 12 o'clock midnight. I usually turn off. Okay? I use .edu, but really, I don't know why I start with the KAIST.edu, but that's the only one I'm using. I don't use ac.kr. Okay, for introduction or the general, the major you are dealing when you conduct experiment or not, you are dealing like measured quantities. You are dealing always the time history record, something like displacement, velocity, or accelerations, or temperature variations. Whatever you're dealing with the phenomena, usually you are dealing with the time history, the record. Then once you get that time history record, same thing on strain, pressures, and all that, then the basic quantity you have is such a time domain data. Then now you are in the position to do something to make the quantity for the engineering sense. Then you have to really discover a lot of different things you want to discover, and that's what usual measured quantities, okay? And the physical phenomena, of course, I'm dealing with a random phenomena or stochastic phenomena. But there are only two different types of the phenomena exist in the world. Whether you like it or not, two different kinds. Simply yes or no. For example, that two quantities is very clear. So here, as phenomena, whether the things is deterministic or the random or stochastic. Only two different phenomena exist. If that phenomena falls in deterministic, then that's not the random, which is day and night. Just if it's not day, it's going to be a night. Some of you could say, no, what about 5 o'clock in the morning? It's not night, it's not day, it's between. I could classify that as a night. So two different phenomena. So deterministic phenomena and the stochastic or random phenomena. For the deterministic phenomena, motion predictable. It's a deterministic. You know exact orbit of the satellite. So it's a very, very deterministic quantity for the position of the satellite. And usually you can use time domain or time history analysis. That's what the deterministic quantity. For example, motion of the pendulum, right? Motion of the pendulum is predictable. Then if you could say, what about the air resistance? Or if you have air as environment, of course you can compute the air resistance, and still you can compute the period or frequency of pendulum motion. But pendulum eventually will, whether you like it or not, is going to stop due to the damping in the system plus damping, resisting kind of the forces in the environment. So motion of the pendulum, very much deterministic quantity. Response of structure systems, ocean systems, that to harmonic motion is predictable. Due to the harmonic motion. What does it mean, harmonic motion? Like a sine, cosine, excitation function, or combinations, or deterministic excitation. The harmonic quantity, harmonic motion, if its excitation is harmonic motion, then you can predict. It's all deterministic. The reason I'm going to go through the deterministic is, if it does not belong to deterministic, then it belongs to the stochastic. Very clear. And the record is repeatable. You can generate. So it's like a vibration testing or noise testing, noise relevant testing. All that kind is repeatable. But any transient phenomenon, the stuff that I'm working on with the students, a shock problem, underwater explosion problem, strictly speaking, it is repeatable, but it's very costly to conduct explosion testing, like the 10,000 pound explosive placed underwater and put the ship, let it detonate. Very expensive. One shot could cost like $100 million. $100 million is how much in Korean won? 100 million. 천억? 천억. That's 100 million, not 천억. 1억 is 10 million. Right? 1억 is, you figure out. One is always a problem. So, but record is repeatable. That means it's really deterministic phenomena, quantity can be repeatable. If it's repeatable, that's a deterministic. No, that's not true. Reverse is not true. But now stochastic or random phenomena, unpredictable. You measure the turbulent pressure at the tip of the airplane. You fly the airplane at 10 o'clock in the morning today. Then you record the turbulent pressure. The next morning, same time you come, you take a measurement. Third day, you take a measurement. If you look at it, it's all different. It's not predictable. So, if it's not predictable, that doesn't mean that, well, I have to give up. No, that's not true. So that's what the stochastic analysis is come into picture, to do the beautiful things using the statistics. I'm going to give you all the basic statistical quantities you can perform using the record you could have. Ship motion subjected to the sea wave. Sea wave. You took the course last semester from Professor Choi, right? About the wave, about the ocean wave. Okay? Then you can generate the wave train, which could be repeatable, but strictly speaking, ocean wave, I don't believe is a repeatable quantity. Could be easily, you can say, that's the random quantity. How to handle? How to handle the quantity which is unpredictable, then by the wave train, that means one segment of time history of the wave, then you generate the ocean, the structure systems response, then what can you say in general? So that's, this course may guide you. I don't want to see you, oh, this is not contained in the course coverage, so I cannot do it. What I want you to do as a KAIST students, I'm gonna teach you 1, 2, 3, 4, 5. Then I want to do all the way from 1 to 100. Too much? No, not too much. I want to teach you up to 10 maybe. Then you can do the rest of the 90. So completing the 100, you can do it. You can do it. One of my thesis students, I was very disappointed. Why? Before he tried to solve the problem, he has preset mind already. No, I cannot do it. That's too difficult. You have to jump over that sort of the barrier. Think this way, if you cannot do it, who else can do? Right? if I can not able to do it, who else can do it? So that barrier you have to remove from your heart right now. I want you to teach you up to 10, then I want you to handle the rest of the things. That's what the research come into picture. Okay? And nowadays, of course, gust wind is a big problem in US. Hurricane. Here, typhoon. Problem. Every summer you have a problem. In US, they have a problem all the time for hurricane problem. Just to wipe out the whole thing. Tornado problem. Just the whirling sort of the what do you call that, wind? Touch down on the ground and take off, and touch down, take off. It just wipe out everything around where the wind touched down. Tornado. Earthquake problem. Korea experienced earthquakes, I heard them years ago. When I say earthquake, I'm talking about the Richter scale higher than 4. 4 very small. US we are dealing with 8. It destroys everything. In 1989, I was in the office and I was about to sit on a chair, then bang! And I can see that precast concrete beam is shifted like this. I can see the motion. How long? It, as I recall, is something like a 15 or 20 second. 15, 20 seconds, I felt at that time, it's like 1,000 years. It's just moved forever. Disaster, earthquake. So earthquake is random in nature. 2 earthquakes occurred in different locations, never the same, which is really so-called non-stationary. Non-stationary means each individual record is very, very unique. There is no resemblance. So that's what the stochastic phenomena is. So stochastic phenomena, then I want to really show you what I know about the stochastic phenomena. And of course, every week or every other week, I'm going to give you some homework. Otherwise, you have too much time just doing nothing, right? No. I want you, as you take this course, I want you to really, nowadays you have a beautiful tool called internet. Internet search, you can find anything. So that's what you should use it. I ask my students, would you find all this through the internet? I don't have any saved record in my computers. She found everything I asked for. It's just everything she found in the internet. That's amazing. It's amazing. Even my paper, some 20 years old paper, I don't have a record. And I asked Yonok, would you go find it? She found it. It's amazing. So then keyword, you put the keyword. So same thing. So now the stochastic, the name, random, the name, maybe not, it's somewhat strange. Check out the internet. Tons of the literature publication is out there. Very simple. The way I do lecture, some of you know already, I repeat the same thing over and over and over until you fed up, saying, Professor, stop, that's enough. Then it stays right here. If I talk just once, it comes right here, and it just goes right out and evaporate. So that's the way I do. Random data analysis, time domain analysis, of course, then getting into the spectral analysis, which is a frequency domain analysis. Why I do this? Why you do that? All the engineering analysis. You do a lot of different things using time domain, like histories of the data. Then you manipulate, throw into the frequency domain. Why you do that? In vibration sense, you all took the vibration course. Then in the vibration course, if you always conduct a modal analysis, right? Why you perform the modal analysis? Why? You could say, teacher never say that. That's why I didn't do any modal analysis. Nonsense, right? Why you do the modal analysis? Sidetrack. Where is Kang-hee today? Kang-hee? Kang-hun.
He go business trip.
Business trip. Where is he? Oh. Okay, that's a good point. Think of this. You all came today. If I don't walk in, do you feel good? Then go home. In the class time, if I can not come in, I will at least send you email ahead of the time, right? Sorry, gentlemen, Young-shin is not able to make it today because I'm in Seoul. Mutual respect, Yun-suk, right? You drink too much last night. No, I'm not saying that. Then I couldn't wake up in the morning. I have to sleep whole day through. Then hell with Young-shin. I can't make it to attend the class. No, you for the mutual respect, you could at least send me an email or 문자. You always has a 문자, right? Then you can send the 문자, right? You're so fast, you can send the email, 문자, for about 10 seconds. So let's do that in the future. So unpredictably, if you can make it, then just send right there 문자, just a few words, then I know where you are, right? Rather than just disappear. Would you do that? Let's do that. That's for mutual respect, nothing else. And do you know that? The KAIST, the regulation you call, requires to write the attendance record. I never ever do this, but KAIST request all the attendance record. I don't know why, but graduate students we usually don't do. But at the end of the semester, they said, "Where's the record?" Why you do the modal analysis? Sidetrack. I'm checking what's the level of learning you have done for the course. In this case, it's a vibration which is a continuous into the random vibration, random analysis, stochastic analysis. What would be the reason? 주성. What's the reason? You do modal analysis, right? For the vibration class, right? Yes or no? You heard about modal analysis.
I think free analysis is very costly and hard to analysis. So we just do assumption, with assumption, and modeling is easy.
Jusong explained the level up here on the vibration level, way up there, not the ground level, but way up there. Ground level, not clear. Up here. Chongwan, why you perform the modal analysis? Directly connected to a dynamic analysis of the FEM model. Why you do? You took the vibration course in undergraduate, and last semester you did. What's the reason to conduct a modal analysis? No? What about Gust? I like him, that guy. You know, he never missed a class. Gust, what would be the reason?
To know the response of certain things.
Okay. I don't know your name. And Youngpil? Go-Young-bin. What would be the reason? I told you in the class we can talk anything. Didn't I say that? Just to feel free. Just to feel yourself comfortable. At the beginning, I want to tap in your heart, you know, whether it's all good or bad or drunk a little bit last night. That's what I want to know. Where? Good. It's very good. So every answer is, I could say right. I could say very good. But you missed a big point, you see. So when I take the course, I want you to capture the essence of it. Core importance of the subject. Okay, you talk about the beautiful vibration, all that. My answer is correct. Good. Very good. You missed the core. What you explained is, when I just date, oh, that's the woman. I don't care whether she's beautiful or not. I just date and have a good time, and may marry, may not, so on. But you miss the core. So before it's all single, married. 재범 married. 주성 single. All single. So you really need hard work coming up. When you marry, when you date, mostly the reason I really date was that time in US in mid-1960s, there were not many girls at all, Korean girls. It's hard to find the girls to even date. But here you have so many girls in the same floor here, you can date, right? When you really date with it's all man here, woman, then you want to really see whether your hobby is the same, or you can really spend the whole life together. So personality, how it responds with myself, whether it could resonate or not. A lot of different things you want to investigate, right? Most important thing is frequency level has to be the same. Otherwise, she wants to do this, then say, I don't want to do that, I want to do this. All the frequency level could be different. So you want to, through the modal analysis, you want to find out the personality means basic character, the vibration characteristic. You want to find out the systems, the vibration characteristics on it. You have to know the dynamic characteristics. The basics of dynamic characteristics is modal frequency. And the mode itself, at the first mode, second mode, third mode, vice versa. And second, another reason that Chusong mentioned about to make the life easier, to simpler, for the cost, all that. So if you throw the system in the physical domain, if you throw that into the modal space, this the system in the physical domain is all tangled up. It's all interconnected. When you throw this into the modal space, everything is all single. It's all single mode, a bunch of single mode. Then you can perform this in a one time, this in another time, vice versa. You can handle one modal system at a time. But in the physical domain, you have to deal, everything has a tangled up situation. In other words, complex coupled system. In the modal space, everything is all decoupled. To do that, you have to find the natural frequencies and modal shape. That's the main reason. I'm not sure that I explained good or not. That's the way you handle. So, time domain analysis as a coupled system as is. When you throw that into the frequency domain, then characteristic shows. I can tell in what frequency it resonates. Vice versa. So always, when you learn, think this way. What does it do? Modal analysis, example, I just pulled the example. What does it do? That essence you must understand. You must investigate. Otherwise, you lose the important essence. And what else you're going to try? So do that. At the beginning, as usual, my lecture goes pretty slow at the beginning to put the basis a little bit solid. Then we can move out the taxiway. Then up to the point we get it on the runway, it's slow. It's all the prep. And when you get into the runway, then we can take off. Okay? All right, so I'll see you Friday. Yeah, Friday, 1 o'clock. That's a graduation day. So we'll see you anyway, 10 o'clock. I'm sorry, 1 o'clock on Friday. Right?
I graduate.
Oh, you graduate, right?
Yeah.
You graduate, you have to go, right? Yeah. So, How many of you you have to go a graduation ceremony on Friday? Let me think. We have a time still. Then if there is any change, I'll let you know by tomorrow. You have to go, period. Yeah, you have to go, right? But we could switch the time. Then I have to let Mr. So know. So, okay. So I'll decide before end of today how we're going to handle that. Okay? Alright, so I'll see you as of right now, the Friday, 1 o'clock, but it could change. How many of you say it's okay to change the time? It could be after 6 o'clock, not Friday, maybe some other day.